In this video, my goal is to illustrate how x86 architecture manages the stack as we make function calls. Remember, the stack maintains or keeps track of the local variables and the parameters of a function while the function is executed. So these variables will be automatically allocated when we make the function call, and they will be automatically deallocated when we return from the function. That's why parameters and local variables are called automatic variables. In x86, the stack is managed by two registers, EBP, called the base register, that points to the base of the call frame of the currently executing function, and the stack pointer, ESP, that points to the top of the stack. Furthermore, the stack grows from larger addresses towards smaller addresses, so it's upside down. That's why I assume that the base pointer register's value is 100, which is a larger address, and the stack pointer is 92, which is a smaller address. So as you can see, I am assuming that the local variables of the caller function, the caller of main, has already been pushed to the stack, and we made a call from within that stub function, in a sense, to the main function. That's why the return address has already been pushed to the stack. So the instruction pointer is kind of pointing to the first assembly instruction within the main function. Because we are starting to execute the main function, the first thing we have to do is to move the base pointer to point to the base of the call stack of main. To do that, I need to first store the old value of the base pointer into the stack. I do that using the push instruction. So the first instruction, if you look at the assembly output of this C code, is push EBP. So I need to kind of make a copy of the old value of the EBP base pointer into the stack. So that's push EBP. That's the instruction that's going to get executed. Obviously, when you push something into the stack pointer is now going to get decremented by 4. So it's now 88. The next thing I need to do is to move the base pointer to where the current stack pointer is, which will be the base of the call stack for main. So I do that using move EBP ESP instruction. So what this is saying is take the value of the ESP register, which is 88, and copy it into the register EBP. That's why they both point to the same location now. The previous two instructions, push EBP and move EBP ESP, establishes the call frame for the function main. Now I need to move on and allocate space for the only local variable that main has, which is x, which is 4 bytes, because that's an integer. The way to allocate space for x is to simply say subtract ESP4. So if you just move the stack pointer 4 bytes down from 88 to 84, we are allocating 4 bytes on the stack. The next statement in our C code is x is equal to add 2, 3. So we are making a function call to a function named add that has two parameters, a and b. So that means we need to supply two arguments. And we are supplying the arguments 2 and 3. In x86, by default, all arguments to functions are passed in the stack. So they are pushed to the stack from right to left. So we need to first push 3, and that's the next instruction. So as you can see, push 3 simply pushes 3 into the stack, and that's going to be the value of b when we start executing function add. Obviously, when we push the value of 3, the stack pointer is now 80 because it needs to move 4 bytes down. Next, we need to push the argument 2. That's going to be achieved by the instruction push 2. As you can see, that's going to be the value of the parameter a when we start executing add. And again, the stack pointer moves 4 bytes down. Now we can make the function call using the call instruction. So that's what we do. Call add. That's the next instruction in our assembly code. Obviously, the call instruction is going to push the return address onto the stack. Return address is the address of the next instruction after add that we are going to return to when we return from the add function. Now the instruction pointer is pointing to the first instruction of the add function. And when we start executing a function, the first thing we are supposed to do is to establish the call frame for that function. How did we establish the call frame for the main function? We first pushed the base pointer, right? And that's what we're going to do. This time the value of the base pointer is 88 because it's pointing to the base of the main function. So we make a copy of this value onto the stack. And the next thing is move EBP ESP. So now we have to move EBP so that it points to the base of the add function, because we are now starting to execute the add function. The next thing we are supposed to do is to allocate space for the local variable ANS of the add function. Because ANS is an integer and that occupies 4 bytes in memory, we simply say subtract ESP 4 by moving the stack pointer 4 bytes down. Now that we have allocated space for the local variable ANS, we need to initialize it to 0. That brings a new question now. How do we know the address of the variable ANS? And that's where the EBP, the base pointer, comes into play. The instruction we are going to execute to initialize ANS to 0 is to say move to the memory location pointed to by EBP minus 4, 0. So why EBP minus 4 to refer to the local variable ANS? If you think about it, the base pointer EBP is pointing to the base of the call frame for the function that we are executing, which is add in this case. And the first local variable will be stored 4 bytes down from the base pointer. That's why the EBP minus 4 would be the address of the local variable. And you can see it in this example. So EBP is equal to 68 in my example. And the address of the first local variable ANS is 64. If I just subtract 4 from this value, I'm getting the address of the first local variable. I don't have it in this example, but if I had another local variable, let's say x, that would have had an address of 60, and that would have been EBP minus 8. And the third local variable, if we had it, would have been EBP minus 12, and so on. So you can now see that the purpose of the base pointer, that's like an anchor point that we use to get the address of the local variables and also the parameters. So let's now look at the parameters A and B. What do we see? We know that after the base pointer, on top of the base pointer, we've got the value of the old base pointer, which is 4 bytes, and then the return address, which is on top of it. That's another 4 bytes, so that's 8 bytes. So that means the address of the parameter A would be EBP plus 8, so 68 plus 8, that would be 76, and that will be the address of parameter A. And the address of parameter B would be EBP plus 12, because EBP plus 12, 68 plus 12, that's 80, and that will be the address of the parameter B, the second parameter. And that's what we do next. So because now we need to move into the computation of A plus B. So we need to retrieve the value of A, store it in a register, and that's what we are doing in here in this instruction. Move EAX from this memory location. So go to the memory location EBP plus 8, so 68 plus 8, that would be 76, and that will be the first parameter A. So bring that value and put it into the local register EAX. So I'm bringing that value 2 and putting it into EAX. Next, I need to get the value of B, the second parameter, and then add it to the value of A, which is now stored in EAX. I do that using the add instruction, so add into EAX the value stored in this memory location, which is EBP plus 12. So EBP is 68. If you add 12 to it, you get 80, which is the address of B. As you can see, the parameters now are addressed using EBP. Local variables are also addressed with respect to EBP. So EBP plays a very crucial role in accessing the local variables of a function and the parameters of a function. In different architectures, you would see the same register appearing, like in MIPS. This is called the frame pointer. Here in x86, it's called the base pointer. But every architecture must have a register similar to EBP or frame pointer that points to the beginning of the call frame of the currently executing function, because the architecture uses that frame pointer register as an anchor to refer to the parameters of the function and also to the local variables of the function. All right, so we have computed our add instruction. So the value of EAX is now 5. And I need to store this value back into the local variable ANS, answer. So how do I do that? Which is simply a move instruction. This time, the value, the destination is EBP minus 4, which is the address of the local variable ANS. and the source is the register AX. So I'm taking the value in AX and putting it into the local variable ANS. Now I am going to move into the return answer statement, the last statement of the add function, and return the value that's stored in ANS back into the caller, which is main in this case. In x86, 4-byte return values are returned in the EAX register, the accumulator register. So I could actually have an instruction here where I move the content of the local variable ANS back into the EAX register, but EAX register already contains the return value 5. So I'm going to omit the extra instruction to copy the value that's stored in answer ANS into the EAX. All right, now we are ready to return from the function add back into the main function, which was the caller. All right, so the first thing we need to do is to get rid of all the local variables because they were automatically allocated when we entered the add function. Now we are returning from add, so we need to deallocate the space that we have allocated for the local variable ANS. It's very simple to do that. All we have to do is to move the stack pointer back into where the base pointer is, because base pointer is pointing to the base of the call stack for the add function, right? So if we just do move ESP EBP this time, so I'm copying the value of EBP into the ESP. So now ESP is also equal to 68. That kind of wipes out all the space that we have allocated for the local variables. Next, I have to restore the base pointer value so that the base pointer goes back and points to the base of the main function, right? And that we do by saying pop EBP. So now, if I do pop EBP, we're going to pick up the old value that we stored in the stack, which was 88, and store it back into the EBP. So EBP becomes 88, kind of points to the base of the main function. And the next instruction that we execute is the return. So we executed the call instruction to jump into the add function. We're going to do the reverse operation, which is the ret instruction. Ret instruction is going to pick up the return address from the stack so that the instruction pointer jumps to the return address, which was the next statement after the call to the add function, right? We are now back in the main function, and the instruction pointer is pointing to the next instruction that we are supposed to execute. So what do you observe? The arguments that we passed to the add function, 2 and 3, they are still on the stack and they have to be removed, correct? Who's going to remove them? Obviously, the main function is going to remove them. So if we need to remove 8 bytes from this stack because we had 2 parameters, A and B, both were integers and both occupied 4 bytes on the stack. And we need to simply wipe them out by saying add ESP 8. So if we add 8 bytes to ESP, so the stack pointer is now 84. So that kind of wipes out all the 2 values, the 2 arguments that we pushed onto the stack. As a side note, I should mention that it was possible for the callee, the add function, to actually remove the parameters from the stack when it was doing the return instruction. That's another way to do it. These are 2 different function call conventions, the C style, and the other one is called the Pascal style. In the C style, it is the caller, the main function in this case, that pushes the arguments to the stack, and also when after returning back, it's the one that removes it by an instruction like this, by saying add ESP8, because it had 2 integer parameters, a total of 8 bytes. So it's the caller that removes them. We could have actually had the callee, which is the add, that removes them by simply supplying a parameter to the return instruction. If it instead of saying return, we could have said ret 8. So in that case, the ret instruction, the return instruction, would have removed 8 bytes from the stack. So when we return, we did not have to execute this. So I'm going to leave it as an exercise to you to think about, as a food for thought. Why you would choose one calling convention to the other calling convention? There are trade-offs, as you can imagine. And C chose the the first calling convention, where it's the caller that removes the arguments. And Pascal, for example, chose the second one, where it's the callee, the add function, that would have removed the arguments from the stack. All right, now that we are back in the main function and we have removed the arguments from the stack using add ESP8, we still have to copy the return value into x, which is the local variable in main. Remember, the return value is stored in the accumulator, the EAX register in 86. So we now have to copy the value that's stored in EAX back into x. So how do we address x? Again, we use the same idea. The base pointer EBP is now pointing to the base of the call frame for the main function. And if we just subtract 4 from it, that's the address of the first local variable, which is x in this case. So it's very simple. Move into the memory location pointed to by EBP minus 4 from the register EAX. So take the value stored in EAX and store it in this memory location, which would be 88 minus 4, which is 84. We are now ready to return back to the operating system with a return value of 0, indicating that this process is terminating without any errors. How do we return a integer value from a function? We know that we are using the accumulator or the EAX register in x86. So I need to put 0 into EAX, and I do that using the move instruction. I say move EAX 0. That puts 0 into the EAX register. Now, before I return from the main back into the caller, I need to destroy the call frame for main. Remember, I need to do the reverse operation. So I need to first wipe out the space that I allocated for the local variables of main, which is just the integer variable. And it's very simple. You wipe out all the local variables with just one instruction, which is move ESP EBP. Remember, EBP, the base pointer, is pointing to the base of the call stack for the main function. If I just copy the value that's stored in EBP into ESP, now ESP is also pointing to the same location. That means I have, with one instruction, I have wiped out all the local variables. So, in this example, I have just one local variable, but assume that you had 10 local variables. You could have just wiped them out with just this one statement by saying move ESP EBP. That wipes out the space that you allocated for all the local variables of this function. Next, we need to restore the old value of the EBP by saying pop EBP. That takes the value that's stored on the stack and puts it into the EBP. So EBP is now equal to 100 in this example. That's the base address of the call stack of the function that made a call to the main function. And finally, we need to execute the return instruction, which is read. That needs to take the return address from the stack, puts it into the instruction pointer so that we can now continue executing the function that made a call to the main function. And that is supposed to call the exit system call to terminate our program. So let's execute the return function, the return instruction, and that takes us, that wipes out the return address on the stack. And that's how the stack looks like. And of course, the instruction pointer is now pointing to the next instruction to execute in kind of the stop function that the operating system has kind of inserted into our code that made a call to the main function. And that stop function is supposed to execute the exit system call to terminate our program. So here is the entire set of x86 instructions for the main function. We start by establishing the call frame for main. We push the parameters. We make a call to the add function. After we return, we remove the parameters from the stack, and then store the return value in the local variable x. Put the return value from the main function 0 into the EAX. Remove the call frame, and then return. And this is the set of x86 assembly instructions for the add function. Again, anytime you start a function, you have to establish the call frame with these two instructions. And then before you return, you do the reverse operation of removing or destroying the call frame for that particular function. All right, I hope that this video makes it clear how a typical architecture like x86 manages a stack in hardware. So the main takeaways are architectures typically use two registers, a stack pointer that points to the top of the stack, and a frame pointer that points to the bottom of the call frame for the currently executing function. Base frame or the frame pointer is very important because architectures use the frame pointer or the base pointer to get the address of the parameters to the function and also to the local variables of the function. If you have any questions, please leave them in the comment section and I'll try to answer them.